Right, so this is lecture number 10. Okay, so mechanical properties. Okay, the concrete may undergoing multi-axial stress. Okay, when we compress the cylinder, the concrete specimen only under the vertical load, the concrete will fail caused by the tensile stress generated in the horizontal directions. Okay, this is because when you compress the materials, it will try to expand. How much expansion depending on the Poisson's ratio. Okay, for concrete, the Poisson's ratio is around 0.2, 0.18. Okay, because concrete is very weak under tension as a result, the concrete will fail because of this tensile stress in the horizontal direction. If the concrete is under multiple axial stress, okay, for example, we have lateral tension, so that will cause the concrete to crack earlier. As a result, the F'(C) will be lower. If the lateral is compression, so that will reduce or offset the tensile stress caused by the compression in the vertical direction. So as a result, that will produce a higher F'(C). Remember when we talk about when we do a compression test, how much friction provided by the steel plate will affect F'(C) for the same reason. Okay. Right. So this slide is showing us how the concrete will behave under biaxial compression. Okay. Which means on the vertical, we have compression, and also horizontally, we have compression too. Okay, so depending on the ratio of sigma 1 and sigma 2, as we can see from here, compression, we call that negative. Okay, so -1 over 0 means the sigma 1 is compression, but sigma 2 is 0. So we have no compression in the horizontal direction. Okay. And then the next one is -1 over -1, which means sigma 1 and sigma 2 will be the same compression. Okay. And then we have around 50% compression in the sigma 2 direction, in the horizontal direction. Okay. So what we can see from here is okay, if we increase the peak stress, under higher compression in the horizontal direction for sigma 2, okay, so the peak stress will increase. Okay, you can see from here, epsilon 1 will increase, and also the peak strain, which is the strain level at the peak stress, also increase. Interesting part is the highest strength occurs at the sigma 2 level around 50%, okay, not at the highest sigma 2 level. Okay, so the higher compression actually is beneficial, but it's not the highest sigma 2 will generate the highest peak stress. This case showing us combined tension and compression. All right. Okay. So sigma 1 is compression. Okay. So I think there's an error shown in this figure. So the arrow should be facing down for sigma 1. Okay. Because sigma 1 is compression. Sigma 2 is tension. Okay. So arrow direction is to the right. So under compression in sigma 1, sigma 2 is under tension. Okay. Again, showing us 4 different levels. Okay. Sigma 2 is from 0 to 5% to 10% to 20% tension. All right, so what we can see here is if we increase the tensile stress for sigma 2, okay, the peak stress, strength and peak strain will decrease. Okay, so that does make sense because tensile stress in the horizontal direction will make the concrete crack earlier. Okay, so the peak strength and the strain will both decrease when we increase the tensile stress at sigma 2. And here shows the case of biaxial tension. So sigma 1 and sigma 2 are both under tension. Okay. So because concrete is very weak under tension, the behavior will be different from the previous 2 cases. Okay. All right. Again, we have 3 different sigma 1 to sigma 2 ratio. Sigma 1 does not change, but sigma 2, it changed from 0 to 1 to 55%. Okay. So what we can see from here is for all the cases, the tensile strength does not really change. Okay, the strength does not change. So the tensile strength is unaffected by the multi-axial stress under biaxial tension. Okay, but the peak strain means the strain level at the peak stress will decrease when we increase the sigma 2, when we increase the tension, tensile stress in the horizontal direction. Okay, which means the concrete become more brittle. Okay. And here shows the triaxial loading. Okay, triaxial loading means in the vertical direction we have compression. Okay. In the horizontal direction, we have compression in all directions, not only sigma 2, but also sigma 3. Okay. So for all direction in horizontal, it is under compression. This is similar to the situation when we put the concrete under compression and when we have a rebar confining the concrete inside the column. Okay. Let me draw something for you. Let's say we have a reinforced concrete column. Okay. So for this column, we have rebar. So this is the column. And the rebar goes in the vertical direction and around the core of the concrete. Okay. And we call that rebar confining rebar. Okay. So for concrete inside the core, okay, it is under situation similar to what we just discussed. Okay, three-dimensional or triaxial loading. Vertically, it is under compression. Horizontally, it is confining from all the direction. Okay, because we have something like this. The rebar is confining the concrete from expansion horizontally. If that's the case, so here shows different situation. The confining strength will increase from 0 to 2 to until 29 megapascal. Okay, and here shows the longitudinal stress, which is the stress in the vertical direction. Okay. So what we can see here is both the peak strength and the peak strain will increase when we increase the confining stress. So the highest peak stress and peak strain occurs at the highest confining strength of 29 megapascal. Okay, so that is good. Another thing we can notice is after the peak stress, the concrete can still resist quite a lot of load. Okay, at the end of the curve, okay, the stress level is not going down to 0. That means the concrete can still resist some load. And we call that residual strength. And that residual strength increases with the confining strength. Okay, so the higher confining strength, the residual strength will also be higher. Okay. Actually, depending on the confining stress level, okay, if the ratio of confining strength over F prime C, the strength of concrete is less than 15%, okay, 0.15, the failure mode of the concrete will be similar to normal concrete. Okay. If the confining strength is higher than 15% of the F prime C, then there's no localized crack. Remember, when concrete crack, we call that a localization damage or localized damage, which means in certain areas of the concrete, the cracks will open up. In other areas, the crack will not open up as much. Okay. So when the confining strength is more than 15% of F prime C, there's no localized damage. And here shows the tension testing. Okay. For concrete, we do not have the direct tension test because to do the direct tension test, the machine need to somehow grab the concrete specimen. Okay, and that grabbing setup will affect the stress level, inside the concrete specimen. Okay, so direct tension is not often done in concrete because of this grabbing stress will mess up the result. Okay, so instead of a direct tension, typically we do the so-called split cylinder test. Okay, so we have concrete cylinder, so we compress the concrete specimen, the cylinder, along the diameter. Okay, and the stress level in the majority of the diameter is under tension. Okay, only the top and bottom is under compression. Okay, and these two equations showing us the stress level sigma 1, which is tension, and the sigma 2, which is compression in different part. So based on that, we can figure out what is F prime SP. SP is for split tensile stress. Okay. So again, on the cylinder, the majority part of the cross section is under uniform tension. Only the top and the bottom part is under compression. Okay, so from split tensile test, we get the idea of the tensile strength of concrete. For flexure strengths, okay, like the concrete beam, we could do a central point, which have two supporting points, and then the load is coming from the middle. Or we could do the third point, support, and we have two load in the 1/3 and the 1/3 part. Okay, so half P and half P. Here shows the stress level of sigma. Okay, M is the moment. Okay. C is the the distance between the neutral point, which is the middle part of the beam, to the point of interest, because along the cross section, the stress level is different. Okay, and I is the moment of inertia. Okay, and depending on the setup, the sigma we can calculate accordingly. And the moment of rupture, or MOR, okay, can be calculated based on one of these two equations, depending on the setup. Because the stress level along the cross section is very different. In the middle part, it is 0. The highest tension is in the bottom part, and the highest compression is the top part here. Okay, and because the strain gradient means the strain level and the stress level are different depending on the location, the point of interest. Okay, so the moment rupture will be higher than direct tensile stress due to the strain gradient. Okay, that is because the concrete is not a pure viscoelastic. It's not a pure elastic materials. It is viscoelastic materials, and that will somehow estimate the tensile stress. All right, this is again the setup for third point setup. So we have steel ball, apply the load, and also the steel rod support at the two ends. Okay, so that means the support will only provide vertical load. There's no moment resistance. Okay. And same thing for the location where we apply the load. And here shows the assumed stress distribution, which when we assume concrete is a pure elastic materials. The blue line is actual stress distribution. Okay. As we can see, because the concrete is not pure elastic materials, the actual stress, the peak stress level will be lower compared to by assuming the concrete is pure elastic materials, the red line. Right. And here shows us if we cannot measure some of the mechanical properties, such as the E value, the tensile strength, or the fracture strength, we can roughly estimate that value based on the F prime C, the compressive strength of concrete. Okay. For example, the E value, we could use that equation, which is a function of rho. Rho is the density of the concrete, and F prime C. Tensile stress, okay. Fracture strength, or Poisson's ratio of concrete is around 0.18 to 0.2, depending on the the mixed design. So before we talk about viscoelastic property of concrete, let's first review stress and the strain relationship of the pure elastic materials. Okay, this is the basic information. Stress, we call that sigma, is equal to force F over cross-section area A. Okay, and F prime C is the measurement of the maximum stress the cylinder, the specimen can resist. Okay, and the strain, we call that epsilon, is the change of length over L0, which is original length of the specimen. Okay, depending on it is compression or tension. Compression, that L will be negative. Okay, tension, the length will increase. And the E value, elastic modulus, we call that E, is the ratio of the stress, sigma over the strain, epsilon. Okay, so that is the slope of the stress and the strain curve. For pure elastic materials, that curve will be a straight line. Okay, that means the E value does not change depending on the level of stress. For concrete, we know it changed over time. And the Poisson's ratio is the absolute value of epsilon y, which is the strain in the y direction, the horizontal direction, over the strain in the vertical direction, or the direction of the load, epsilon x. Okay, so Poisson's ratio is always positive. Okay. If it is under multi-axial stress, then we can consider the contribution from the stress in x, y, and z direction. Okay, so sigma x is stress in the x direction, sigma y and z is the stress in the y and z direction. Okay, and this is Poisson's ratio. Okay, pay attention, the stress level could be positive or negative. And here shows the shear modulus. The shear modulus G is a function of modulus of elasticity, the E value, and also the Poisson's ratio. This is for, again, pure elastic materials. And the shear stress, we call that tau. Tau is equal to G times alpha. Gamma. Gamma is a shear strain. And the volumetric strain, which is defined as the change of the specimen in volume. So final volume minus initial volume divided by the initial volume. Okay, we call that epsilon V. V is for volume. That can be estimated based on the strain in x, y, and z direction added together. Okay, and again, the strain y and z direction could be positive or negative depending on the you apply the compression or tension for the x direction. Okay, and if the stress level in all the x, y, z direction is the same, it is similar to hydrostatic stress. Okay, which is the case in the bottom. Right. And then we have a so-called bulk modulus, which is again a function of E value, the modulus of elasticity, and the Poisson's ratio. Okay. So this is a review of elasticity principles. Okay. For concrete, we know it is not pure elastic materials. Concrete is so-called quasi-brittle materials. Okay. For metals, we call that ductile materials. Okay. So in the beginning, we have the elastic region. After the peak load, the resistance will increase when we increase the load, okay, such as steel. For brittle materials such as glass, okay, initially it also has the elastic region, okay, but the inelastic region is almost non-exist. Okay, so very small inelastic region before the material failure. Okay, so glass belong to a brittle materials. Okay, rubber is also ductile materials. Okay, for all these type of materials, initially it will have an elastic region, which means the curve is somehow straight. The E value does not change. After that, it will have an inelastic region. For brittle materials, the inelastic region is very small or non-exist. Okay. For concrete, okay, we also have an elastic region, but after around 30% of FMC, the slope will become smaller. And after the peak load, the concrete will fail, but not fail suddenly like the glass. Okay, it will have some resistance to deformation until the final failure. And toughness is defined as amount of energy required to fracture a specimen. That is how much energy the material can absorb before final failure. Okay. And energy is equal to force times distance. So based on the areas underneath the load and the deformation curve, we can calculate the toughness for different materials. For example, the toughness for the mantle will be the areas underneath the curve. Okay, so we can see the mantle has very high toughness compared with concrete, because for concrete, the areas underneath the concrete curve is much smaller. Okay, so we can see from here. So again, for all the materials, initially they will have elastic region, which means the curve is straight, the E value does not change. Okay. After the elastic region, if the resistance increase, the stress level increase, we call that strain hardening materials. Okay, for example, steel. If the resistance decrease, we call that strain softening materials. So concrete belongs to strain softening materials. If the resistance does not change, we call that elastic, perfectly plastic materials. If it has no inelastic region, we call that brittle materials. For example, glass. All right. So I just said concrete is not pure elastic materials. Concrete is a viscoelastic materials. So what does that mean? Okay. So let's see these three virtual experiments for three type of materials. The first one is pure elastic materials. So let's say at time t1, we apply the load, and then at time t2, the load is removed. For pure elastic materials, at T1, when we apply the load, the deformation is instantaneous. So the strain is suddenly increased to this level, and the deformation does not change until T2 when we remove the load, and then the strain will go back to 0. Right? This is a classic elastic materials. Right? So what is viscous materials? For viscous materials, when you apply the load at T1, the strain is not instantaneous. Okay, the strain will slowly goes up until T2 when we remove the load, and then the strain will not go back to 0 immediately. Okay, it may keep at the same level or it may gradually reduce. So both the deformation and the recovery is time dependent. Okay. For concrete, it has both the elastic region, or we call elastic component, and viscous component. At time T1, part of the strain is instantaneous. Okay. Like here, a part of the strain is time dependent. It's slowly going up. At T2, when the load is totally removed, part of the strain is totally removed immediately, like in this part, but part of the strain is slowly recovered, like in this part. So both deformation and recovery is time dependent, such as concrete. Okay. For viscoelastic materials, how fast you apply the load will affect its response. Okay, so for example, if you apply the load or the strain rate is fast, even though you do not change the load level, okay, for slower loading, okay, the deflection will be larger compared to fast loading. Okay, this is for materials with viscous component. Okay. This figure shows us if we do not change the stress level, so keep the same pressure on a specimen. If the material is pure elastic materials, then we know the strain will not change. Okay. But for viscoelastic materials such as concrete, the strain will slowly goes up because the viscous component, the strain will be time dependent. And we call that creep. Okay, creep means under the same load, the strain will slowly goes up. Okay. Relaxation means if we do not change the stress level, we keep the same. Oh, no, sorry. We do not change the delta L, so we keep the same strain level. Okay. If that's the case, the internal stress will be smaller. We call that relaxation, sorry, because the stress level is reduced, it's relaxed. Okay, so both creep and relaxation occurs in concrete. Okay, and we can measure how much creep and how much relaxation for the internal stress in concrete. So depending on load level, the deflection will be different. And if we apply the same load, the strain will slowly goes up. And if you keep the same delta L, the strain level, the internal stress will slowly goes down. And we call that relaxation. Here shows the long-term loading and how the effect of the long-term loading affect the curve. Okay. So this is the relationship between the short-term and long-term loading strengths. The x-axis is the concrete strain. We have 1, 2, 3, 4 different cases. The first case is t equal to 20 minutes, which means we apply the load only for 20 minutes versus t equal to 100 minutes versus we apply the load for 7 days versus we apply the load all the time. Okay, so what we can see is, the shorter we apply the load, the higher the ratio of the concrete stress to the cylinder stress. Okay, the longer we apply the load, the concrete stress level will be lower. Okay, that means if the concrete will experience longer time of loading, we should reduce the level of loading because the quick. Okay. And also the concrete strain will increase over time. And here shows the repeated uniaxial loading. Okay, for example, we apply the compression and then we release the compression. Then for the second cycle, we apply the compression again. And here shows the stress and the strain curve. Okay, so in that case, the concrete will accumulate additional stress, a strain. Okay, for example, after the first cycle, the strain is not going back to zero. After the second cycle, we have even more strain, even though the stress go back to zero. We still have some of the strain. Okay, so this is because for the 1 and 2 cycles, we have some minor cracks. So the strain will never go back to zero again. Okay, so micro cracking and also viscous behavior. Remember, concrete is not a pure elastic materials. That will explain why the strain will not go back to zero. And another thing is the peak stress level will also goes down. So after each cycle, the stress level the concrete can resist also slowly goes down. Right. Okay. So we showed these slides many times before. For concrete, before it go to the viscous behavior, it has elastic region, which is around 1/3 of I prime C. The curve will be a straight line. Then after crack is generated in concrete, the E value will become smaller and smaller. Okay. And then we have more cracks generated until the final failure, okay. Which is when in certain location the cracks will open up. Okay, again, around 1/3 or 30%, we have very small cracking in the weakest area. Okay, for normal concrete, the weakest area will be the ITZ, as shown here. For high strength, it could be the aggregate. And then between 30% to 70%, the cracks will open up. We have more cracks, and in certain areas, the crack size will open up. Between 70% to 100%, the cracks in certain location, not all the location, will opens up, and that causes the concrete to fail. And we call that cracks localized. Okay, so cracks in certain location are growing much larger than other location. In other location, even though we have cracks, but the concrete can still resist some load. As we can see, after the peak load, there's no sudden failure for concrete. This is very important and beneficial for concrete. And that's how we can make reinforced concrete. Here talk about ITZ. I think we mentioned about this before. Okay. So concrete strength depending on paste. We have 3 different zones: the paste, the ITZ, and the aggregate. The strength of concrete depending on the weakest of the 3. Okay. For normal concrete, ITZ is typically the weak region. And the shape of the aggregate, the texture on the surface of aggregate will affect ITZ or the bonding. Okay. Reduce the water cement ratio, or if we use silica film, the bond strength of the ITZ will increase. Okay. A different E value between the aggregate and cement paste will lead to cracking, when the concrete is under compression or tension. Okay. For cement paste, we only have one component, one paste. So there's no ITZ, there's no aggregate. So the crack will be more brittle compared to concrete. Okay. For concrete, depending on weakest region, crack will first generated in ITZ or the aggregate. Okay. And then the crack pattern will not be as straight as in cement paste. For mortar, it is somewhere between the paste and the concrete because mortar has no coarse aggregate, only a small sand. Okay. Again, here shows the localization concept. When the concrete is damaged in a peak load, the damage zone is only limited to certain location. Okay. In other location, the concrete can still resist some of the load. Okay. And as I just mentioned, the post-peak behavior is very important. Here is why. Okay. So let's say we have the reinforced concrete beam, and the beam is under bending moment. Okay. The reinforcement is the green line. The gray area is the concrete. Okay. So in the bottom section, it is under compression, and the stress level is somehow like this. The top portion has the highest load, okay, and it will reduce to 0. Okay. So if the top portion is damaged, okay, the whole concrete will not fill. Okay. So the stress will change somewhere like this. Okay. Even though the top portion, the stress becomes 0, but the concrete can still resist some of the load. So the concrete together with the rebar will resist the moment after certain part of the concrete crack. Okay. And same thing for the column. This is the reinforced column. If the concrete cracks, the remaining part of the concrete can still work with the rebar to resist the load. Okay. And for this is the continuous beam or slab on grade, slab on the beams, columns. Okay. For a certain part, the concrete may crack, but the moment will redistribute it because of the cracking. Okay. But the reinforced concrete slab will still be able to resist the load. So that's why we see the post-peak behavior is very important. After the peak load, after certain part of the concrete crack, the whole system, the whole reinforced concrete can still resist load. And different type of concrete the post-peak behavior will be very different. Okay, as you can see here, for high-strength concrete, typically it will be more brittle compared to normal concrete. Although the high-strength concrete has higher strength, okay, as we can see here, the peak load is higher compared to normal concrete. But after the peak load, high-strength concrete will be more brittle, not much resistant after the peak load. Okay. If we put fibers, fiber will increase the post-peak behavior quite a lot. Some of the fiber can increase the ductility of the concrete or increase the toughness of concrete. Some of the fiber can increase even the peak load also. Okay. So when we discuss fiber reinforced concrete, we'll see how the percentage of fiber, the diameter of fiber, and even the size, the length of fiber can change the behavior of the concrete. Yeah. All right. Okay. So today we discussed, the mechanical property of concrete, and we discussed how does crack develop during failure. Okay, depending on the weakest link. Okay, the feeder mode could be different. Okay, and depending on how many directions we apply the load, only vertically or both vertically and horizontally, or if we have a confining strength in other direction. Okay, so the feeder mode will be very different. Okay, and concrete is a quasi-brittle materials. Okay, it is very brittle, but after the peak load, the concrete can still resist some of the load. This is because of the so-called post-peak behavior, okay, and the localization concept. Okay, so yeah, that's the end of